Welcome to the lectures on chemistry. This is a series of lectures brought to the benefit of engineering and science undergraduate students under the program called the National Program on Technology Enhanced Learning. The program is funded by the Ministry of Human Resource Development to all the Indian Institutes of Technology and Indian Institute of Science. And in the first phase we have been creating a large number of web and video based courses for the benefit of teachers and students outside of the IITs to many private institutions and government colleges. In this series of lectures on chemistry, I have been examining the basic principles of chemistry, particularly physical chemistry, and this is a series of modules. The current module in which I have been lecturing for the past 7 or 8 lectures is known as the molecular spectroscopy module. Today we will continue with the vibrational or polyatomic infrared spectroscopy with the emphasis not on the normal mode as we did in the previous lecture, but on what are called the local modes and the group frequencies, and will give you a little bit about how infrared spectroscopy is employed in the laboratories in actual practice. Today on the lectures on molecular spectroscopy, today's lecture is on polyatomic, vibrational. We are looking at infrared radiation for infrared spectroscopy, and we shall look at what are called group frequencies or local vibrational modes. It is an extremely important subject in vibrational spectroscopy. The fact that we talk about local vibrational modes as opposed to normal vibrational modes means a fundamental distinction to begin with. The local vibrational modes can be anharmonic, they can be very large amplitude vibrational motions, as in the case of a ring torsion that you saw in benzene in the last example, or in trinitrotoluene where you saw the methyl group rotate fairly with a large amplitude, fairly significantly. It is a low frequency mode, but it is a large amplitude vibration. A large amplitude vibration essentially means that the forces associated with them restoring the vibration back to the equilibrium, the forces are not necessarily linear in the displacements. Forces being linear in the displacement is how you understand the harmonic motion, leads to a harmonic potential in the form of a parabolic curve, and then we are able to solve this as a beautiful oscillations pertaining to very standard amplitude, periodicity, all those things. Now if a molecule vibrates and in a single vibration, when it goes to a very large amplitude, simply decides to rupture because there is sufficient amount of energy, then there is no harmonicity of oscillations backwards. The molecule has dissociated. The carbon hydrogen bond, for example, associated with methane in the presence of chlorine in sunlight, elementary organic chemistry tells you, gives you the CH bond breaks, it is abstracted by a free radical, and then what you have is the CH3Cl being formed, and that is a bond rupture. The bond breakage can happen through electronic excitation, energy transferred to the local bond which stretches, and eventually the atom gets pulled out. Such motions, which are very large amplitude vibrational motion, if you talk about it, in a single vibrational mode the molecule can break away. Those are anharmonic vibrations. There are vibrations associated with bonds and also energies associated with groups of atoms. Like very familiar example for you is the functional group that you talk about in organic chemistry, phenolic group, carboxylic group, the carbonyl group. the acetyl group. Different groups have, you can identify them as species oscillating with respect to the rest of the molecule and contributing to a local absorption, resonance absorption, and these resonance absorptions on these different groups will show a characteristic spectrum, which is what we call as the local mode spectrum or group frequency spectrum. So local modes, when we discuss, are inherently anharmonic. Now let me give you a typical example of a spectrum before we start looking at the specifics. Okay. What I have here is the spectrum of benzene, the structure of benzene. This is the transmittance, the absorption 1 by the absorption is the transmittance here percent. The transmittance percentage is given from 100% transmission, which means no absorption, to less and less transmission. Therefore this can be converted into absorbance. This is nothing but quantifying the intensities, absorption intensities, and on this axis what you have is the wave numbers. Here the wave numbers decrease. This is the smallest, 400 centimeter inverse. You will not be able to read these numbers, so let me give you the numbers. This end is 400 centimeter inverse vibrational, and this end is 4600 centimeter inverse, and in between you see the scales 400, 800, 1200, 1600 and so on. This is the axis of increasing wave numbers from right to left, and what you see is a typical absorption line at about 3000, 3200, between 3000 and 3100 there is a significant absorption. Then there is a very large absorption near about 900, this is 650, 680, 700 centimeter inverse, this is about 700. So you are looking at an absorption frequency corresponding to about 670 centimeter inverse. There is another major absorption peak at about 1500 centimeter inverse. So let us list them down to see what we mean by group frequencies. Okay. Benzene, there are 3 vibrational frequencies, large absorption frequencies. What are the values? There is one at about 3100, between 3000 and 3100 centimeters. Centimeter inverse. Okay. Then there is one around 1600, no, around 1500 centimeters, approximately 1500 centimeter inverse, and then there is one at about 670 centimeter inverse. This one, this is 800, this is 600, so roughly 670, 660, 670 centimeter inverse. 3 frequencies. Now let me take a molecule which is close in structure to benzene. Let me take the structure of toluene. Okay. This is, sorry, it goes outside the range. This is the IR spectrum of toluene. Toluene, which is C6H5CH3, one extra methyl group. Okay. Now let us look at the spectrum of this and see what features are similar to what we have near the benzene. 1, again we have an absorption near 3000 to 3100, around that centimeter inverse IR, but except that now it is a multiplet. We have again absorption near about 1500 centimeter inverse. You remember this? Near 1500 centimeters. We have one around 3000 centimeter inverse, but with a much more let us look at it with a much broader absorption, or there are overlapping absorptions here. And then we also have one near 670, that 680 centimeter inverse, and again at about 750 you see additional lines. Okay. So what you see is for toluene you see lines similar to what you will see in benzene, but in addition you see extra lines due to possibly the oscillations of CH3. Now if we have some doubts about this, if we look at the structure of the infrared spectrum of the next compound, this should be, let me find out, this is mesitylene, this is meta, this is basically 1,3-dimethyl benzene. Let me, okay, 1,3-dimethyl benzene. So what you have is 1,3-dimethyl benzene. So what we have is we have one more group CH3 and a CH3, and let us look at the spectrum of this compound. Again what you see is near 3,100 centimeters, around this area there is a large absorption, and you see this pattern is pretty close to the pattern of the previous compound, namely toluene with one methyl group instead of two methyl groups. Here there are two methyl groups, there is one at position 1 and position 3 benzene. You see a pattern similar to that, and again you see the absorption frequency near 600 and 700 and something, 670, 680, and also a large significant absorption around these areas, but there are additional frequencies which appear, which were not there in benzene, which are not there in toluene, but which are there in metaxylene. Now what is the point of all of this? Point of all of this is that pattern recognition, if you think about it, is how a majority of chemists would approach spectroscopic techniques, particularly with respect to identifying compounds. So now you have a series of similar compounds, benzene, toluene, and then metaxylene. Of course you can extend this to other compounds, I am only picking up the idea. You identify patterns which are common to that of the benzene ring, you identify patterns which are common to the benzene with respect to a CH3 stretching. This is a local CH3 group oscillation with respect to the benzene, and then when there are two such groups that they interfere with each other or they interact with each other, and then the pattern slightly changes and so on. Therefore what you have is a series of compounds giving you similar spectra which can be identified as spectra or components frequencies due to specific groups present in the molecule. Okay. Now let us go back to the basic picture of what is meant by local modes. Local vibrations corresponding to various groups. For example, for two areas that we can concentrate or around 4,000 to 1,300 centimeter inverse, this is one section, and the other area where we can look for vibrations which are characteristic of the compound are between 900 and 650 centimeter inverse. Now remember from the previous pictures, the last lecture, remember the progression that we had. Torsional vibrations, the plane of the ring or the plane of the atoms in a ring gently getting distorted is a very small frequency. Then we have the bending vibrations, atoms or a bond angle getting shortened and lengthened, a bending vibrations of slightly higher resonance frequencies, infrared frequencies, and then of course then the stretching vibrations which correspond to the actual stretching of a very strong bond. Therefore the force constant is very large. If you remember the old picture of normal modes, So we had them grouped in that order. Now obviously when you look at this 900 to 650 centimeter inverse, we are going to look at the frequencies or absorption which distort the equilibrium structure by distorting the planar or distorting the what is called the torsional modes. Torsional modes are basically modes in which a group of 3 atoms in one plane versus group of 3 atoms in another plane, and how they basically rotate with respect to each other. So that is of a lower frequency, which you will see pretty much in this. Then the high frequency end 3100 here, 4000, this is corresponding to stretching of the carbon hydrogen bond. CH bond is one of the strongest bonds in organic chemistry, 90 kilocalories, 94 kilocalories, huge amount of energy, and therefore stretching that bond is going to require a large amount of energy, and what you see at the high end is the stretching frequency, and in between you will see stretching of various groups which are not highly non-polar bonds, or the what is called the highly covalent bonds versus ionic bonds. If you look at, or semi-ionic bonds, you see that a whole range of frequencies fall in this region. Okay. Let us list some of these numbers for your convenience. Okay. You will have a group frequencies. These are experimentally observed. Carbon H stretching frequency, typically in alkanes, that is saturated hydrocarbons, you will see approximately absorptions in the range of 3000 to 2840 centimeters inverse. These are observations based on many molecules, millions and millions of molecules, and over a period of time spectra have been tabulated, and such tabulations are available for libraries and for the chemistry laboratories. So here is the stretching frequency of alkanes in that range. The asymmetric, then again in the stretching there are symmetric and then asymmetric stretch. Symmetric stretch approximately 2900 centimeters inverse, and the asymmetric stretches between 2800 to 2850 centimeter inverse. This is the usual stretching frequency that you find for the methylene groups and for the carbon hydrogen groups. Okay. Then there are what are called the scissoring motions, scissors, scissoring motion. Then there are rocking motions. What is meant by rocking? Keep shaking the base, okay, rocking motion. Then there is wagging motion for group frequencies. Okay. Dog's tail wags with respect to the rest of the body. Okay. So there is a small group of atoms which sort of oscillate with respect to the other. The bulk of the molecule remains pretty stationary, whereas of course the molecule never remains stationary in a genuine vibration, in the sense the center mass remains constant, but every part has to compensate for the motion. But the bulk of the group, which is very small reduced mass oscillating a large, and the large reduced mass of the rest of the group not showing up much, so it looks like a part of the body is oscillating like a tail wagging, dog's tail wags. Okay. Then what are there is also twisting motion. These are all various types of molecular motions. Okay. The twisting motion is, you remember what you do for a twist. Most of you who wash clothes will have to twist it sometimes in the absence of the dryer and the modern day gadgets. Many of us have twisted the clothes to take the water out, so basically twisting it like this. Okay. So parts of the molecule which rotate with respect to the other part which rotate in the anti direction, that's a twist. This is a twist. Okay. So there are different types of molecular motions that one can observe in what is called this general infrared spectroscopy. It is very hard to classify them as only normal modes or only local modes, but whenever they are referred to a group frequency, I would like to put them as the local mode, because that refers to a local group. Okay. So typically, where do these various frequencies come in? Scissoring motions, the range is between 1460 1470 centimeter inverse. Rocking, very low frequency, about 700 to 720 centimeter inverse. Wagging and twisting, rarely somewhere between 1350 to 1150 centimeter inverse. You have seen some of these examples in the previous case, but let me try and see if I can find one of those examples here. Yeah, the spectrum, the IR vibrational mode that I have here in the screen corresponds to, this is the methyl group. So this is toluene with the two nitrogens groups here. This is the nitrogen nitro NO2 groups here, NO2. So it is 2,6-dinitrotoluene. Is a low frequency vibrational mode. What you see here is 1195. Even though these are normal mode frequencies, you can see significantly that these three hydrogen atoms moving relative to the rest of the body looks like this is, if you call this as the end of the tail, or I do not know whether it should be called tail wagging, but it falls in the frequency range of about 1150 to 1350 that we talked about. So there is a small part of the molecule moving relative to the rest. Okay. This is one example, and the other group vibrations that you can see here, even though this is normal mode, what you see is largely one group vibrating relative to the other. Let us see this. If I have a torsional motion of the benzene, the toluene group somewhere here. Okay, now what you see is this is the in plane out of plane motion of the nitro groups. 178. No, what we are looking for is, yeah, here is a torsional motion of the methyl group relative to the rest of the ring. So this is a torsional vibration. So likewise we can identify groups and groups of frequencies. Okay. Now let us continue with the classification of some of these frequencies in order to complete this lecture. There are many molecules for which we can sit down and look at the vibrational modes one after the other. Normal mode picture is one thing, but now let us group the frequencies for what are called group frequencies. Okay. Now I talked about the alkanes and the methyl group vibrational frequencies earlier, and we got sidetracked into scissoring, rocking, wagging and twisting and all those things. Please remember that molecular analogies are very interesting anyway. Let us look at the conjugated polyenes. Conjugated polyenes. You know what this means. What this means is double bond, alternating, single bond and so on. Double bond, single bond, double bond, alternating, a double, single, double, single, double, single. Such alternating bonds are called conjugated structures, aromatic hydrocarbon, the hydrocarbon structure, and conjugated alkenes have symmetric stretch. For 1,3-butadiene, for example, approximately 1650 to 1600 centimeter inverse. These are patterns characteristic of symmetric the conjugated diene structures. Then you have for alkynes the C triple bond C the vibrations or stretching vibrations are approximately 33, 33, 32, 67 centimeter inverse, and the CH bending vibrations around 700, 610 centimeter inverse. Okay. Now let us just look at some of the groups, functional groups for a change, and let us list the functional group frequencies which are very important in IR spectra. The functional group, when you look at the phenolic group or alcoholic group, OH or hydroxyl, the absorption frequency is between 3650 and 3580 centimeter inverse. Then molecules with hydrogen bonding of course will have a slightly reduced frequency because the OH is stretched by the presence of another O here, slightly weaker bond, and therefore what you have is the vibrational frequency for this OH group gets reduced a little bit. The CO stretching vibrations or between 1260 and about 1000 centimeter inverse, and the OH bending vibrations as you had seen earlier for water molecule with the other hydrogen here, but in general the bending vibrations for OH fall in the range between 1420 and 1330 centimeter inverse, and likewise you have this C double bond O, the carbonyl group vibrations, the carbonyl group vibrations fall in the range between 1600 to 1400 centimeter inverse. For a variety of compounds, the carbonyl group can be a ketone, it can be from an aldehyde, or the CO group frequency may be in the environment of a carboxylic group, or it can be in the acyl chloride. The typical each CO, depending on the environment in which it is in, shows up at a slightly different frequency, and therefore one can obtain a series of these spectra, take the fingerprint and then identify the patterns in them, and using these patterns from unknown compounds we can try and identify what kind of functional groups are present in the molecule. Okay. This is what we do with respect to the infrared spectroscopy of some of the organic compounds as we see in liquid state. Now what is important is in the solution state when we do this spectra, liquid meaning that these are dissolved in some solvents, and then you take the spectrum of these compounds, the infrared spectrum of these compounds in solution states give rise to these kind of frequencies that you have seen, which are quite different from the infrared frequency of these compounds in the gas phase, where the interactions between the different molecules is minimized, and also in the gas phase a large part of the spectra are cluttered by the rotational, the coupling of this molecular motion with the rotational motion of the molecule, because in solution phase the rotational motion averages out, we do not see them in and also the infrared spectrometers that we have for solution phase have a very poor resolution, that is they are of the order of 1 centimeter inverse, is 1 to 2 centimeter inverse is what you see as a normal laboratory IR spectrometer. Gas phase spectra are much more highly resolved depending on the spectrometer that we use, and also they give rise to additional features of the vibrational lines in the form of rotational structure, substructure to this.